Hello, welcome to Tech Talks.
Hello, and welcome to today's session of sleep power recovery. So, this sleep power recovery scheme, this is also used for a three-phase induction machine, and as I have discussed in my earlier lecture, that it only works with SRIM, slip ring induction machine. That means where you have an access to the rotor side. So how does this slip power recovery scheme looks like, and what is the basic principle is that the air gap power that is PG, this is actually divided into two parts. One is that which one is converted to mechanical power PM, that is 1 minus S of PG, and the other part that is lost in the rotor winding, that is SPG, it is lost in the rotor winding. Or the rotor power. So this SPG, if you look at this SPG, this power is going to increase if your S or the sleep increases. So this sleep increases when you are running the motor at very low speed. So when you are going to have a speed control at very low speed, so there is an effective loss of power. So we will see ways so that we can feed this power back to the grid, so that we can feed this SPG power back to the grid. So that is only the slip power recovery. This is the slip power occurs because of this one, important because at low speed it is highly significant, and we will see of certain things that how we could feed this sleep power back to the grid so that much reduction in power loss happens. Okay, now the diagram for this one is we are having a stator, okay, for much better understanding I am drawing the stator and the rotor diagrams differently only for this case. This is R, Y, B, this is small r, this is small y, this is small b. So it is connected to here. RYP is connected to the grid. This is the grid, three-phase grid. Now this is the rotor side. Since it's a slip ring induction motor, this is the rotor side. So this rotor side voltage is connected to a three-phase diode rectifier. Three-phase diode rectifier. So now this part is AC, this part is DC. Obviously this will be positive and this will be negative. Now this DC will be converted to AC by a thyristerized inverter. So this thyristerized inverter, this has three parts. This side is AC. So three lines will come out of here. Now these three lines will be connected to a transformer. Okay, so this is the primary winding of a transformer, or the low voltage side of a transformer, and this is the high voltage side of a transformer, iron core transformer. Now this high voltage side of the transformer is again connected to the grid. Now here I have left this space intentionally blank. Here the reason for this is that from the previous lecture you can easily find out. Here we can connect two things. One is that we can connect a capacitor over here, or we can connect an inductor over here. Now which one we will be connecting, that is a choice. Now what determines that choice? The selection of this device determines the choice. When we are using an SCR, so SCR has a property that if you turn it on, it will be remaining in on condition until and unless you apply a reverse voltage across it. Whereas IGBT MOSFET, they can be easily turned off by using a negative gate pulse. So since this is a current control device, so in this side a current source is an obvious choice. It is operating as a current source inverter. It is CSI. So when it is operating as a CSI, then adding an inductor is an obvious choice. So we will be adding an inductor over here of LD. Okay. A resistance is also added over here, but this is of negligible value. It is RD. Remember that this in the resistor is of negligible value. almost equal to 0. Now going through all this, that this is the line voltage VL, this one is the line voltage VL or Y. This one is the line voltage VL, that means this corresponds to same voltage. This point and this point corresponds to same voltage. Now the turns ratio, this is the stator, this one is the rotor. The turns ratio between the stator and the rotor is T1, T2. And another thing is that the winding factor of this one is KW1 and KW2. Now what we will be getting in this part, that is RY, this part we will be referring to this one as VRR. That is line voltage of rotor, that is VRR, line voltage of rotor. This side voltage we will be referring to as VDC, and this side voltage we will be referring to as VI, V inverter. Similarly, this line to line voltage we will be referring to as VT. All these are line to line voltages, and the turns ratio for this transformer is N2 N1. This side is a high voltage side, and this side it is low voltage side. So from this diagram you could easily make it up that from this side power can enter the motor from this side, and it can go all the way in this direction. But if you try to feed power from this side, you cannot do that. Why? Because suppose you are feeding power from this side, here you are getting an AC. This one will convert your AC to DC, but when it will convert your AC to DC, then this side will be positive and this side will be negative. This diode will not conduct. All of the 6 diodes present over here will not conduct. So no power will be transferred in this side. Only way power can be transmitted is in this direction. Okay, so this is the DC link inductor. So this is the diagram for the slip power recovery scheme. Now we will be going to some analysis of this part. So before going into the analysis, be clear of some points that this steady stateized inverter can only operate in inverter mode. This SCR can only operate in inverter mode. That means the alpha is the firing angle. The firing angle this alpha can only operate from 90 degree to 180 degree. Because from 0 to 90 degree this alpha operates, then this thyristor will be operating in rectifier mode. Only after 90 degree it will operate up to as an inverter mode. So this is only the available range of alpha. Certain things you just keep in mind. Okay. And whenever we are talking of power, that is Vi cos phi, when phi is more than 0 to less than 90, then cos phi is one to 0. When this phi is 180 degree and it is more than 90, then cos phi is 0 to -1. So in this zone, in this second zone of operation, this power is becoming negative. That means it will be giving back power to the grid. That means we will gradually see that the angle between this voltage and current per phase, that will be more than 90 and less than 180 for the successful operation. So moving to the next some part, that is analysis of this one. This page number 7. That when we talk of this VRT, that is VRR, when you talk of this VRR, that is the voltage across the rotor line to line. Okay, so this is actually equal to what? This is actually equal to VRR is slip voltage of the stator part. Okay, multiplied by some ratio. This ratio is what? That ratio is winding factor into turns ratio divided by winding factor and turns ratio of the stator. This one you can easily find it out from the EMF equation of an induction machine. From the EMF equation of an induction machine you can easily find it out. Now this one we will be calling it as A. It is kW2 T2 by kW1 T1. We will be calling it as 1 by A. So this is RR. VRR 1 by A. So this VRR, this one reduces to SVL. This is slip. S is slip. by A. Okay, so this is the AC voltage that we have got. Okay, now the DC voltage, rectified DC voltage, you refer to the diagram, that the DC voltage VDC is equal to what? VDC is equal to 1.35 VRR, that is 1.35 SVL by A. Now, if we go to the other side of the equation, other side of the figure, that is here you can see VI. If we consider from this side, calculating from this side, so if we consider calculating from this side, that is from VT to how we reach VI, then what we will get is that VI is equal to 1.35 VT cos alpha. VT cos alpha. Okay. Now, how this VT can be addressed as? This VT can be addressed as N2 by N1 VL. It is line to line voltage. So this one now becomes what? VI now becomes what? VI now becomes 1.35 N2 by N1 VL cos alpha. So we have got two equations. One is this VDC and the other is this VI. So if you look at the figure, this VDC and VI, there are two components in between. One is this inductor and another one is this resistor. So if you neglect this resistor, then no power is lost in this inductor, because inductor, capacitor, these two are lossless components. No power is lost in this inductor or capacitor, only power is lost in resistor. So considering a lossless system, you can put this VDC equal to VI. Okay. You can also change this equation before putting to 1.35 NT, it is the turns ratio for transformer, VL cos phi. If you put on VDC over here, you see 1.35 VL, this 2 will cancel out. So in VDC you are left with only S by A, and here also 1.35 and VDC will be cancelling out, so you are left with only NT cos alpha. So this S is equal to A NT cos alpha. So the required speed is omega r 1 minus S omega S. Out of all this equation, if you put it over here, 1 minus A and T cos alpha omega S, if you look at this equation, so if you want to change the speed omega r, if you want a speed control of this induction motor omega r, then you don't have any control on this part. You don't have any control of A and NT, but you have any control on this alpha, that is the firing angle of the inverter. So you can easily control this alpha to change the speed of the motor. Now, if we try to calculate that what will be the torque, then it is equal to P by 2 into PG by omega S. Now this rotor power, that is the air gap power, that is equal to what? That is equal to VI ID by omega S. What is this ID? This ID is actually current going in this direction. It is ID, DC current, DC link current. By S omega S, because this power is will be multiplied by a ratio S. Now if you go on putting the values, you will be reaching that P by 2, this is the number of poles, this is actually the pole pairs, 1.35 VL ID by omega S A. So this is the torque equation that you will be getting over here. From this torque equation, this is the per phase. If you want to get the 3-phase torque equation, total torque value, then you have to just multiply this one with 3. Now next, coming to the phasor diagram, that how the voltages and current would look like. if this is the per phase voltage, fundamental of the per phase voltage that you are giving to the motor, then this is actually 90 degree. So I had explained earlier that the power factor will be from the cos phi, that phi will be from 90 degree to 180 degree. So it will start anywhere from here okay, and it will end up anywhere here. Anyhow, the diagram is something not so symmetric. So this angle will be phi, this will be more than 90 degree. If this is the voltage of a phase, this will be the current of the same phase, fundamental of the current of the same phase. But in actual, this will be looking like a square shaped waveform. That is, it will be looking like a square shaped waveform with effectively two humps. This, how we were getting these two humps, that can be easily calculated if you draw the phase voltages as per given by the rectifier. This can be seen over here. Okay, but if you consult any book, they will be giving you only the fundamental of this part of this current form. Okay, so from this equation you can easily see that whatever power, our main target was that the air gap power that is lost in rotor winding to feed it back to the grid. For that, what we have calculated, for that we have made this diagram or this schematic, this scheme. So the power that was lost over here, that is SPG, we are actually feeding this one to here, but we are also controlling the speed of the motor at the same time. You can see from here that we are also controlling the speed of the motor at the same time, and the power is also fed to the grid. So this is effectively the slip power recovery scheme. So I will be ending my session now. Thank you. We will meet again in the next session.